off in our notes. And the next thing up is two sources in phase in the same medium. Now, key to note that they're in phase, so remember that means the wavefronts are moving together. And maybe we have, based on this diagram here, we have one source starting here and one starting here. I'll use different colors. And these wavefronts move out relative to that source. And now this is important because it creates a nice symmetric interference pattern of maximum and destructive interference. So what we have two sources here, and the solid lines could represent crests, and the dashed lines could represent troughs. So if we look at these different points, well, D, we have two crests here. So you could picture two wave pulses traveling at each other. When those interfere, they're going to constructively interfere and create a large wave pattern. So what we need to do is we need to be able to recognize that D, since it's constructive interference, that would be an antinode. And then if we look at A, where we have two dashed lines, that's actually still constructive interference, because since these are in the same direction, we're going to add those up. So that would create a very large displacement in the negative direction. So that would also be a node. And the key thing here is if we look at spots like point B, where we have a crest and a trough interfering, well, these are going to destructively interfere, and at B would be a point called a node, which, again, node means no interference. So if this were sound waves heading out at point B, it would be destructive interference. So you actually wouldn't be able to hear anything here. And if it were light waves, well, we'd have a very bright spot at D since it's constructively interfering, and so on. Waves, which I did mention because last week I introduced nodes and antinodes. And this is when two waves having the same amplitude and frequency travel in opposite directions through a uniform medium. The standing wave is a pattern of wave crests and troughs that remain stationary in a medium. And common questions that you will be asked about a standing wave is the number of nodes it has and the number of antinodes it has. So, as well as the wavelength of the wave. So, one example you may see if we have two boundary is one set up like this, and the number of antinodes, or wherever you see these spaces that are spread out or constructive interference, so there would be one antinode here, and then nodes are where there's no interference. So this would have two nodes and one antinode, and the wavelength would be whatever this length is. Let's call it length L. So in this wave, we have half a wavelength. So if we say that L is equal to the wavelength over 2, because only contains a crest, one full wavelength would look something like that. So we have to continue it. Well, the wavelength is just taking the inverse of it. So just like cross multiplying, it would be 2L. So if L equals 2 meters, well, this wavelength has a wavelength of 4 meters. And this works for any size standing wave. Let's see. Okay. So another example. It's not perfectly drawn, but just bear with me. So again, if this were L, we have one full wave here. So, or we can think of it as 1.5 waves. Should use a different color. right? That's one full wave, and then we have another half. So there's 1.5 wavelengths in this length, or in fraction form, that's 3 over 2 wavelengths equals L. So this wavelength is 2/3 of L. So to whatever L is, we can just use that quickly. Personally, I just like to look at it. So if this were 6 meters, well, okay, one full wave is about 2/3 of the way there, which is just 4 meters. So that's the wavelength for this example. And we can do the same thing where we count the nodes. Let me use a different color. So wherever we have no interference. So this example would have 4 nodes. And then, wherever this maximum constructive interference occurs is where the antinodes are. So it would have 3 antinodes. And then I'm going to post a video that's pretty cool about resonance, but every body or body of matter or object has a particular frequency at which it will vibrate if disturbed. One thing I always think of when I'm thinking about this natural frequency, because it's very easy to visualize, is a tuning fork. No matter how you strike that tuning fork, once it starts producing that noise and vibrating, it's going to be vibrating at that particular frequency. So if the tuning fork has a natural frequency of 512 hertz, when you strike it, it will vibrate at that frequency. Now, so on. If you have something that vibrates at the same natural frequency of that source and the natural object, if they are near each other, resonance will occur. So resonance is another example of wave phenomena, and I'm going to post a couple of videos that show this very nicely. Wave phenomena that we're going to introduce is diffraction, and basically that's just a spreading of waves into a region behind a barrier that's in the wave's path. So this can allow you to hear sound when you are around the corner of something, or creates pretty cool light patterns. And again, I'm going to post a few examples of this as well. So a couple examples of this. If I have a barrier here with a very small opening, I have wave fronts. So these are going to be wave fronts. As they strike this barrier, they're going to diffract, and they'll create a pattern like this. Now, the smaller the opening, the larger the diffraction pattern. And you can see that because if I do another example, where again I'm use a different color. I have these wave fronts that are traveling in. I have a very large opening. These are going to kind of create a pattern like this. And again, I'm going to post some examples of this so it's a little easier to see than my drawings. Okay, the next part of the waves unit that we're going to look at involves light, and light allows us to see a lot of these phenomena very nicely. Now, it is important to note that the human eye can only perceive a very, very, very small fraction of this electromagnetic spectrum. So this right here is all that our eye can detect. But these are all examples of different light waves. They all have different wavelengths and therefore different frequencies. Some are way too large and some are way too small to measure with rulers and typical classroom materials. Now, the speed of light, which wasn't measured until about 100 years ago, is known as c, and it's on the front of your reference table, and it's going to be 3 times 10 to the 8th meters per second. So it's not going to be a number you have to memorize, but it is important for us to know. And if they're ever talking about the, frequency of a particular light and we want to know its wavelength, well, we can do that knowing the formula for the speed of wave, which we did a couple weeks ago. And that's frequency, f times lambda, or wavelength. But now, since we're talking about light, wherever we see velocity, we can plug in this c. So this formula is going to be applicable to any light as long as it's in a vacuum. Because what we will learn is that the speed of light will change if it's traveling through different objects, like water. Like if a light wave is traveling through water, it'll travel at a different speed than outer space or a vacuum. Last thing we're going to look at for this particular chunk of notes is going to be reflection. And before we do that, ray diagrams are going to be very important as we move forward and study reflection and refraction, which we're not going to get into, so I'm not even going to bother introducing it right now. A ray, it's just a straight line drawn at right angles to the wave fronts used to indicate travel of direction. So if we have a bunch of wave fronts moving to the right, well, the ray would just be drawn perpendicular and show the direction that it's traveling in. The incident ray is the original wave. It's going to strike a barrier or interface, which could be between two small media, but that's not applicable till we do refraction. The reflected ray is the one that rebounds from the boundary, and the normal is just the line perpendicular to the boundary. So here I have my boundary. So the incident ray is going to be this first one. So maybe I want to call it the incident ray. The normal is going to be a line perpendicular. It's an imaginary line perpendicular to the boundary. And then the reflected would be drawn like that. So most of these diagrams we draw will not contain these particular wavefronts, and they'll just have rays. Here you see the definitions for angle of incidence, the angle between the ray and the normal line, and angle of reflection, the angle between the reflected ray and the normal line. Now, very, very important to know, we always measure angles from the normal line. And the normal line, again, is this imaginary line right here, which I'll label. Remember, the incident ray is the incoming ray, so this will be the incident. And this will be the reflected. So whatever angle of incidence, that would be this angle. And then between the reflected ray and the normal, we'll call it theta r. The law of reflection states that the angle of incidence is always equal to the angle of reflection. So if we know that this is 60 degrees, well, then the angle of reflection between the reflected ray and normal is also 60 degrees. There's two types of reflection. Most of the reflection we will look at is regular reflection. So what that may look like, we have a bunch of rays coming in at a nice angle, and then we have them reflecting nice and neat, very organized. When we have a very rough surface, we might see scattered or diffuse reflection. So maybe we have a bunch coming in, and now it's not a regular pattern, so these are going to kind of reflect all over the place in no particular pattern at all.